good to see you all again. So we'll just finish off electricity tonight. We'll go over circuits, resistors, and capacitors. Okay. So I know it's quite confusing to a lot of you, but luckily in electricity and for Physics 191, a lot of the questions are quite repetitive. So every year they kind of ask the same sort of questions, especially with capacitors. Okay, so I'll try and go over some of the common questions that come up. So number one, we have. Oh, by the way, someone hasn't taken. Someone only got one page? Because it's supposed to be 2 pages for both. Okay. Yeah, the stapler wasn't working apparently, so that's why they're not stapled. Sorry about that. So we have an electrical circuit here. We have a wire coming in, and it's going through so we've got 2 currents coming in. So this one is 4 amps and the other one is 3 amps. Okay, so current is the amount of charge that's flowing through a conductor. Okay, so current is equal to the amount of charge, so Q, over time, so the amount of charge that is flowing per second. So here you've got 4 coulombs per second going through this wire, and on the bottom you have 3 coulombs per second going through this wire, and when both of them get to this point here, they're going to add up. So then how much is going to be going through at this point here? So it's going to be the total current going through here will be 4 plus 3. So the total current going through the resistor is going to be 7 amps. Okay. So there's going to be 7 coulombs per second going through this resistor. And what we want to find out is how much heat is being dissipated per second. Okay, so if they talk about rate, it's talking about how much energy is being used per second. So that's going to be power. So power, you get the symbol capital P. So there's, for electricity, you have P is equal to I squared multiplied by R. So I is your current and R is your resistance. So here our current is 7. So 7 squared times our resistance, which is 100. So that would give you 4,900. So 4,900 watts, which is 4.9 kilowatts. Okay, so just divide that by 1,000 to get kilowatts. Okay, so your answer will be E. And on that, I'll just talk about resistors quickly. So you have a resistor, and you say that you have your charge is trying to go from left to right. So it's trying to, the bottleneck is the resistor, so it's hard for the charge to go through here. What that means is there's a lot of friction, and if there's friction, that's going to generate heat, right? So that's why resistors can generate heat, and so that's like how your heaters work. So they're going to send we're going to have charge flowing through these resistors, which generates friction, and that generates heat. Okay. Our next question, we have an electric heater designed to output 1 kilowatt of power with a 220 volt power supply. So that's P is equal to 1,000. So remember that has to be in watts, not kilowatts. Our voltage is 220 volts. And so we want to find out what the resistance is going to be. So resistance is equal to question mark. So we have our power equation. So on my cheat sheet, you'll find P is equal to VI. So power is equal to voltage times current. Power is equal to voltage squared over resistance. And you also have power is equal to current squared multiplied by resistance. Okay, so you have those three equations for power and electricity. So here we have P, V, and R. So we're going to use the second one here. And we're just going to rearrange that equation for R. So R will be equal to, so you'll just swap those two. So R will be equal to V squared over P. Our voltage is 220, so 220 squared over our power, which is 1,000. And that will give you 48.4. So that's ohms, 48.4 ohms of resistance. Okay. Now number 3, we have a circuit. We have 2 resistors. And so these are in parallel. You have your battery. All right, so we have our 12 volt battery. So that's creating the potential difference. So that's making positive charge. So this side, the long line is the positive line. So this side will be positive and the short line will be negative. Okay, so but that's not really too important. And so this resistor here on the left, so I've drawn it slightly differently so that you can see that it's in parallel, but so you can draw these circuits, simplify them, but you should be able to recognize when they're in series and when they're in parallel. So the way that I like to think whether it's in series or in parallel is to trace the path of a charge that's going to travel through the circuit, and if the charge has to go through that resistor no matter what, then it's in series, whereas if it can choose not to go through that through that resistor, then it's in parallel. So I'll give you an example of what I mean. So if I was a charge, I'm going to start off here and I'm going to go across, and then from here I can choose to go either through this side and then come around, or I could choose to go around here and then choose to go through the right resistor and back. So I can go through either one of these two. So these two are in parallel, okay? And so we know that the left one has a resistance of 1 ohms and the right one has a resistance of 10 ohms. So which one's going to have more current flowing through it? The one on the left, right? The one with lower resistance. So you're going to more current. So your current, I, is equal to V over R. So what that means is that it's inversely proportional to the resistance. If you doubled your resistance, your current would decrease by a factor of 2, or it would halve. So here we have 10 times the resistance, so the current through here will be 1/10 of the current through here. Or in other words, the current through resistor 1 will be 10 times the current through resistor 2. Okay? So we know that, so that means that I1 must be greater than I2. Okay, so we've sorted that part out. Now we need to think about the power. So the amount of power that's being generated, so power is equal to voltage times the current. So it's, if you double the current, if you have the same voltage and you double the current, you're going to double your power. So here we know that the current going through, the current going through resistor 1 is going to be 10 times greater. So that means that P2 will be greater than, P1 will be greater than P2 as well. Okay. So because the current is greater, the power is also greater. Cool. So before we go on to number 4, I'll just quickly talk about resistors. So you have your circuit. So let's say that initially we just have one resistor, and the resistance is 10 ohms, okay? And we have a voltage of 10 volts, okay? So this is our just example circuit. Now, the amount of current that can go through is going to be V over R. So that's 10 over 10, which is just 1 amp. So there'll be 1 amp of current going through this circuit, right? Now, what would happen if you now added another resistor in parallel? So now we're adding another resistor in parallel. So now the charge can either go through this one or go through this one. And this one is also 10 ohms. And what that means is that 1 amp, so this resistor was letting 1 amp go through here per second, 1 coulomb of charge go through per second, and this one here will also let 1 amp through per second as well. So you're going to double your current, and if you double your current, your resistance is equal to V over I. So if you double your current, that's going to halve your resistance. So if you have, what that means is that if you have 2 resistors in parallel and they're the same value, you double your current, which means that your resistor halves. So then the effective, resistance is just 5 ohms. Okay. So now that we know that, we'll approach the next question. So you have two 20 ohm resistors in parallel. Okay, so these are both 20 ohms. So what would the effective resistance be for these two? So remember that if you have these two are in parallel, so if you can just divide it by 2 because there's 2 of them, okay? So the effective resistance is the same as having one resistor that's 10 ohms, okay? So now our first pair of parallel resistors is the same as having 10 ohms. And then your second pair, which are both 10 ohms, that's 10 ohms. Okay, so that's the same as having one 5 ohm resistor. Okay. So you can simplify it to the diagram below. So it's the same thing. And then, so now these two are in series, which means that you're just going to add them normally. Okay, so that's going to be 15. So your total resistance, R total, will be equal to 15 ohms. Okay. So that's just if the two resistors are in parallel and they're the same value, you can use that shortcut, okay? But normally, you can prove this by, so normally you'd go 1 over R total is equal to 1 over R1 plus 1 over R2, right? So, but I like to write this as R total is equal to R1 to the negative 1. So remember that R1 to the negative 1 is the same as 1 over R1. And R2 to the negative 1. And then, so put that all in brackets and put a negative 1 on the outside of it as well. So that's, what that means is that you can just do that all in one step on your calculator if you put it in like that. So then if you wanted to calculate that one, do it the long way just to prove it, then you could go 20 to the negative 1 plus 20 to the negative 1, all of that to the negative 1, and that would give you 10 ohms. So you can do that just to prove it to yourself that it's actually true, okay? But once you know that, in the exam you shouldn't have to do that, and you can just say, well, there's two in parallel and they're both the same value, so I'm just going to halve it, okay? Now the next one, we have 3 resistors in parallel. So now we have 3 in parallel. What do you think we're going to do there? So what would he do with these 3 here? Yep, you can divide it by 3. So 100 divided by 3, that's just 33. So you can say we have one resistor here that's 33 ohms, and then you have another one which is 100 ohms. So then these two resistors are in series, which means that the total will be 33 plus 100. So our total will equal 133 ohms. Okay. Sweet. So knowing that will make your life a lot easier. And usually if they put two resistors in parallel, they will make it the same value. All right, so number 6, we'll move on to capacitors. So basically what capacitors do is they store charge, and by storing charge they can store electrical potential energy. So in this case here we have a battery. And we have a resistor, which is our light bulb. Okay, so we have our battery, which is 12 volts, our resistor, which is 12 ohms, and our capacitor. So capacitors have a property called capacitance. So if you have a greater capacitance, it means you can store more charge for the same voltage. And the unit of capacitance is farads. So F-A-R-A-D, and the symbol is F, okay? So our capacitor here is 500 millifarads, so C is equal to 500 millifarads. So milli, remember, is 10 to the negative 3, so 500 times 10 to the negative 3 farads, okay? So we want to know what will happen when the switch is open. It means that charge can't flow through the circuit, so it can't flow. And initially there is no charge on these capacitor plates. Okay, so it says the capacitor is initially discharged. Which one of the following statements best describes what you would observe after the switch is closed? So once you close that switch, now the whole circuit is connected, and that means that the charge, the current, can start flowing. Okay, so your current is going to start to flow. Remember, the long line is your positive plate and your short line is your negative plate. So in electricity, the direction of the conventional current is the direction of the positive charges. So the positive charge is going to go through your resistor, and there's going to be 12 volts of driving force behind that current, which is pushing that charge through this resistor. So that's going to happen immediately, and as soon as the current starts to flow, remember that power is equal to voltage times power is equal to VI, so voltage times current. So that means that as soon as your current starts to flow, there will be power generated, which is going to be light. So the light will come on instantly, and the charge will get to this plate here, but it can't go through because it's not connected, right? So the charge is just going to start to build up on this plate. So gradually, more and more charge is going to build up on this plate. Now, remember that positive charges don't like being next to each other. So there's more and more positive charges coming, but there's already positive charges here. So what they do is they're going to repel. They're going to repel the. There'll be a repelling force in the opposite direction, and there'll also be a voltage. It'll also start to develop a potential difference across this capacitor plate. Okay, so what that means is that the current is going to start to slow down, and if the current decreases, the power is going to decrease, which means that the light will start to get dimmer, right? And eventually, the capacitor will reach the same potential difference as the battery. Okay, so when that happens, the voltage across the capacitor will be equal to the voltage across the battery. So they'll both be 12 volts, which means that there will be no potential difference between here and here. Okay, so between this side and this side, delta V is equal to 0. Okay? And so when that happens, the current will stop flowing. And when current stops flowing, there's no more power being generated, which means that the light goes off. Okay? So looking at our options here, it's going to be either D. So D is the light bulb would come on instantly, which is true, and then go dim over a period of several seconds. Or it could be E. There would be a very brief flash of light lasting much less than a second. So it could be E because if it discharged really quickly, this could actually happen in a very brief moment, like under a second. So we can actually calculate how long it would take for the light to go dimmer. And the way you do that is to calculate the time constant. So your time constant is given the symbol tau, right, like torque. So this is time constant is equal to resistance times the capacitance, so RC. And our resistance here is 12. So 12 times 500 times 10 to the negative 3, which is 0.5. So that's your capacitance. So that's 6 seconds. So time constant is in seconds. What that means is that it's going to take 6 seconds for the current to become 37% of what it was initially. Okay, so after 6 seconds, it'll go to 37%. And then after 12 seconds, it's going to become 37% of 37%, which is 14%. And then after 3 time constants, it's going to become 37% of 37% of 37%, which is 5%. Okay? And usually after about 5 or 6 time constants, you can say that the current is going to be negligible. So 5 or 6 time constants would be about 30 seconds, right? So it's going to take at least 30 seconds for the light to go pretty dark. So it's probably going to be D. Okay? So your answer there is D. Number 7, we have 120 microfarad defibrillator, which uses a capacitor, and it's charged to 200 volts, and it's placed in a RC circuit. So RC stands for resistor and capacitor. Okay, so it's got a resistor and a capacitor in that circuit, and it's got an open switch. So in this case, the capacitor has been charged up. We want to know how much current will be flowing in the circuit when the switch is closed. So current, remember, is I is equal to V over R. The voltage here will be 200. And the resistance is 100. So that's going to be 2 amps. So the answer there is A. Okay. Number 8, we have a defibrillator. It sends a large current through the chest of a patient suffering from cardiac arrhythmia. The defibrillator stores charge in a 50 microfarad capacitor. The initial voltage across the capacitor is 2000 volts. So we want to find out how much energy the defibrillator has deposited in joules. So this is quite a common question. This comes up pretty much like, I think 6 times in the last 11 years this question has come up. So it's how much energy is inside a capacitor. So it's really simple as well. So as long as you know this equation, so U, that's the symbol for electrical potential energy, remember that, is equal to half CV squared. So C is your capacitance and V is your voltage. So here it's half times our capacitance, which is 50 microfarads. So 50 times 10 to the negative 6 times our voltage, which is 2000. So 2000 squared. And that will give you 100 joules. Okay, so that's all you need to do. Really easy. Now we want to find out the time constant. The time constant is resistance multiplied by the capacitance. Our resistance is 400 times our capacitance, which was 50 times 10 to the negative 6. So that will be, so this question is continuing on from number 8. So that's 0.02 seconds. So you want that in milliseconds. So ms is milliseconds. To convert seconds into milliseconds, you're going to multiply this by 1000. So that will be 20 milliseconds. Okay? All right. Number 10. And again, we have an RC circuit. So it's got a resistor and a capacitor. The capacitor is uncharged, so there's no charge on the plates. And when we close the switch, we want to find out how long it takes for the current to drop to 37% of its maximum value. So remember that the maximum value will be the initial value as soon as that switch is closed. So we want to find out how long it takes. So 37%, that's one time constant. So we have something called Euler's number. So Euler's number is E. So if you look on your calculator, if you do shift log, that's Euler's number. Okay, and if you do e to the power of 1, that's just e, right? So that's going to be like 2.7 or something like that, I think. So 1 over e, if you did e to the power of negative 1, that would give you 0.37, which is equal to 37%. Okay? So our time constant, so what we need to do is we just need to find one time constant, which is RC. So resistance is 100,000. So 100 times 10 to the 3 times our resistance, which is, our capacitance, which is 20 microfarads. So micro is 10 to the negative 6. And that will give you 2 seconds. Okay, and then number 11, when fully charged, how much energy is stored in the capacitor? So that's our equation from before. U is equal to half CV squared. So half times our capacitance, which is 20 times 10 to the negative 6, times our voltage, which is 30. So 30 squared. That will give you 0.009 joules, or you could write it as 9 times 10 to the negative 3 joules. Okay? So, yeah, capacitors, the questions they ask you don't tend to be that hard unless it's a concept question. Then it can be a bit hard, but the equations that they ask you to do is usually quite simple as long as you know the equations and know what they're asking. Yeah. Okay. So that's it for the basic tutorial. We finished a bit early again. We'll start again at 8:20 for the advanced tutorial. Okay? All right. Cheers, guys. Hey. Oh, yeah.